616 from Shigley's book. This is about analyzing a shaft under fatigue load. So we have, let's read the statement. We have a rotating shaft in this figure machined from AISI 1020 cold round steel. It is subjected to a force of 6 kilonewton force, as you see here. Find the minimum factor of safety for fatigue based on infinite life. If the life is not infinite, estimate the number of cycles. Be sure to check for yielding. Alright, so before doing anything, we need to look up some material. Some information, some data about our material. Is 1020 cold round steel. We need to know what the SUT, tensile strength, and what the yield is. So let's go to the book. I have to go to appendix number, okay, let me see, where was it? Is it 820? 820. Go here, for 1020. 1020 cold round. You see the tensile strength is 470. We have to write this down. Alright. So SUT is 470 megapascal. I need to know the SY too. The yield point. Okay, the yield is 1020, yield is 390. So let's write this down. Alright, so you're gonna need that later. We have the force 6 kilonewton force acting there. In order to figure out the stresses, we need to do FVD, find reaction forces. So let me see. Yeah, so we have reaction here. I call it R1. The reaction here R2. We have that force 6 kilonewton. Distance from left bearing to the force is, from right bearing to the force is 175. The left one, the total length of the shaft is 500. So 175 millimeter on the right, and the left is going to be 325. Alright, so we found that. But before moving on, we need to label those important points here. So let me label them. So the one important point here is point A, where the left bearing is. Then first shoulder, this point B. Then I have another shoulder here. This is a point of action of our force. Another shoulder here. And then the right bearing, point F. Alright, so with that, okay, so we can do shear force and bending moment diagram. So if you go like this, my force, you need to find forces R1 and R2 first. Okay, to do that, we know that the equilibrium of this shaft, summation of forces in y direction must be 0, and that means that, R1 plus R2 will be 6 kilonewton, and then I take moment about A, and then you find this 6 kilonewton force times the distance from point A is 325 equals, then the right bearing R2 times the entire length, 500. From here R2 will be 3.9 kilonewton, and then R1 will be 2.1 kilonewton. So okay, and then we have to plot, if you plot the shear force, it's going to be 2.1, goes to the right, and then at that point it's going to go down, negative, and then the other side you're going to have 3.9, okay? Alright, then let's look at the moment. The moment, okay, by the way, let me write down the important points. Point A, point B, point C is like here, this is point D, this is point E, this is point F here. So at point D, I'm going to have the highest moment of, and then we're going to have it dropping. So at this point, moment is going to be 2.1 times 325. Alright, so 2.1, 325, so 682.5 Newton meter. That's point B. Okay, so at point C, the moment is gonna be, okay, the distance from A to C, let's see how much that is. From A to C, distance is, you know, the bearing is 20 millimeter and then 180 here. So it's gonna be, actually, moment at point is gonna be 200 times this force here, kilonewton. So 2 times 21 will be 420 Newton meter is the moment there. Okay, so alright, so let's look at them. Moment is maximum at point D, but at that point the shaft diameter is the highest, it's the thickest there, right? So if you compare that point D with point C, look at the point C, the moment is slightly lower, not slightly, is lower, it's 420, but the diameter of the shaft is 35, substantially lower than 50, and then other thing, there is a stress concentration there, and that's going to make things a lot worse, you know, worse when compared to point D. So if failure happens, it's going to happen at point C. Alright, so at point C, we have two things happening. We have a shear force, and also we have a bending moment. Right? Bending moment, maximum stresses are going to happen here and here, but shear force is going to cause maximum shear stress on that line, right? So what I'm going to claim here is that the stresses caused by the moment is going to be worse or bigger. So I'm going to show it to you guys, you know, number wise. So moment, you know, stress caused by moment is going to be my divided by I, right? So how much is my moment at point C is 420. The diameter is 35, the radius is going to be 17.5. Then divided by 1/4 of pi, then radius to the 4th, right? So this is, by the way, Newton meter. Everything else is millimeter. If you want to have your results in megapascal, you have to have Newton and millimeter. So if you convert that 420 to Newton millimeter, I need to have like a 1,000 here at that, right? So if you do that, guys, your bending stress is gonna come out 99.8. Alright, so I did calculate that already. Alright, so 99.8 megapascal. And then for tau, tau max, as I said, is going to happen here. For a circular section, it's going to be 4/3 of V divided by A. So 4/3 of, at that point, we have 2.1 kilonewton. The area, the pi radius squared. So if you calculate this guy, you're going to find your shear stress to be 2.9 only, 2.9 megapascal. So when it comes to failure, it's more likely to happen on outside surface. It's gonna failure happen is gonna because of the bending moment, not because of the shear stress. And as you see, as I said, they're happening on different points, and they are not happening simultaneously at the same point, right? So when the shaft is in this position, maximum normal stress happens here, but maximum shear stress happens here. So they are not happening at the same time, at the same point. So, right? And who is bigger, who is worse is this guy. So we're going to focus only on that. Alright. So by the way, let's see if we look at this point D, how much stress is going to be there. At that point, moment is larger, but the diameter is larger too. So let's see. Let me do that. 682.5 times diameter there is like 50, so I'm going to use 25 moment radius divided by 1/4 of pi times 25 to the 4. So my stress comes out, guys, as 55. Yeah, so it's come 55.6. So it's smaller, right? But as I said, point C is gonna be way worse because not only we have the larger stress, but we have the stress concentration. But for fatigue application, you remember we need to find Kf. So because sigma max is gonna be Kf times sigma, sigma normal, nominal that we found, assuming no stress concentration. So we need to find the Kf. So Kf, on the other hand, you guys know that is 1 plus Q times Kt minus 1. Q was notch sensitivity factor. We need to look it up from the table. Let me, from graph. So let me show that first. Let's see, gotta go to chapter 6. And we had the notch sensitivity there. Okay. Yeah, it must be here. Okay. So Q, we need to find it. We know for our material, tensile strength is 470. So it's going to be closer to this here. My radius of fillet at that point was 3 millimeter. So you come down here, and then 470 is like this. So if you go to the left, it's slightly less than 0.8. But look, yeah, but the material is 470. It is tensile stress 470, so it's slightly higher than this. So if you're here, slightly higher, and then yeah, you go to the left. It's not gonna be 0.8, but okay, this is like 0.7. It's like 0.79, something like that. 0.79, 0.8. So let's say 0.79. 0.79. So Q is 0.79, but we need to find KT. KT, we have graphs at the end of your book. So in appendix number, let me go see it. Which one? Is it A15? Yeah, theoretical stress concentration. So we come here. So look what we got. For bracket with hole, axial loading, bracket with hole with bending, bracket with notch, axial. These are not my cases, right? So go down, shaft with axial load with a shoulder, shaft with torsion, and then shoulder, shaft. This is what I need. Shaft with bending moment and shoulder. Alright, so let's look at it here. Radius of fillet for me was 3. My diameter of the shaft at point C is 35. The smaller diameter, this is not right. So 3 divided by 35. You have 0.08985. So let's say 0.9, like here. But the larger diameter divided by lower, 50 divided by 35, 1.43. So this is 1.5. So we are here. Stress concentration, go to the left. Alright, so this is 1.6. This is like 1.7 almost, right? Something like 1.7. Let's say 1.7. See, on my notes how much I consider for that. I consider 1.7. Okay, 1.7. Then KF will be 1 plus 0.79. 1.7 minus 1. So let's find this guy. 1 plus 0.79 times 0.7, 1.55. 1.55. Alright, so then max stress at point C is going to be 1.55 times 99.8. So then this will be, I have it in my paper. Yeah, I found it's gonna be 150 something. Okay, let's calculate it. 1.55 times 99.8. 155. Okay, 155. This is my stress. So now let's look at your, let's look at what happens. 390 is my yield. This stress, even with the stress concentration, is still less than 390. So what I can say about the yield is that no yield, because this is less than that, right? So no yielding occurs. But we want to we want to see whether we have infinite life or not. For that, we need to know SE. If I know SE, I can compare this guy with the SE. So since it's not given, we have to calculate that. SE is Ka, Kb, Kc times Kd, Ke, Kf, and then Se prime, right? So we need to know what those are. We have to calculate them, right? Ka was surface finish factor. I'm going to calculate that. Kb was size factor. Kc was load factor. Kd was temperature factor. Ke was reliability factor, and Kf was miscellaneous factor. This problem doesn't tell me anything about temperature or reliability or miscellaneous thing. So I'm going to consider those guys 1. For load factor, since this is a rotating shaft and it's, the load is like similar to a Moore's machine, so it's rotating bending, Kc will be 1. So all I need to do is to find Ka and Kd. Surface finish factor, if you remember, was ASUT to power B. A and B depends on your condition of the surface. So let's see what we have about that. It says this shaft is machined from cold ground. Okay, so those are keywords I needed to know. Then you go to your book. Let's go back to chapter 6. see what those what we have about that. Let's go here. Okay, Ka. Where is the Marine's equation? Okay. Surface finish factor. If it is machine and cold drawn, factor A in SI unit is 3.04. Okay, 3.04. Then SUT for us was 470. Right, and then to power B, let's see, power B is negative 0.217. Then we find Ka equal to, Ka comes out 0.8. It comes out 0.7999, but let's say it's 0.8. Kb is the size factor depending on the diameter. So let's go here. Here's my equation. For diameter less than 50 millimeter, is this equation, 1.24 diameter to this power, right? So, okay, let's see. 1.24 times my diameter, which is 35, to that power, 107, negative 107. If you calculate this guy, it's going to come out 0.847, 847. Yeah, 0.848, something like that. Alright, so then, there you go. You have everything. Oh, SE prime, by the way. SE prime, it was first estimate for the endurance limit. We started with 50% of SUT. So it's going to be, for us, it was 470. Half of that will be 235 megapascal. So then, look, SE will be this. Point Ka, Kb, then Kc, Kd, Ke, Kf, all of them 1, then Se prime. So if you calculate this guy, you're going to find Se of 159. 159 megapascal. So our stress is 155, right? Endurance limit 159. This is less than endurance limit, so it means what? We have infinite life. Infinite life, and then we say the factor of safety of 159 divided by 155. We can divide those two guys by each other. This is how we report the life. We say we have infinite life with factor of safety of 1.02, 1.03 or 1.02. Alright, so infinite life. Okay, so this is we are done. But, let's look at other cases. SN diagram, it has two knees, right, and then we have plateau. So we are here right now, our SE was 159 and our stress was 155. So life is infinite. It's gonna be close to 1,000,000, because if you remember, we called the infinite above 1,000,000, we called it infinite. Alright, so but what if my stress was larger, When a stress is, if our stress was less than FSUT and higher than SE, so this is actually FSUT stress. So then I fall in this region. So if your stress was in that region, then my life finite, and I know it's gonna be less than 1,000,000 and greater than 1,000, because that's what we have. If that was the case, then you had to find the life. You know, the life, you can use this equation. Sigma equals a n to power b. And I did an example like this in class. So b was 1 negative 1/3 of log of f SUT divided by SE, and then a was f SUT squared divided by SE. So what f was? F was fatigue fraction coefficient. You know, let me show you the right name. Is, what did we call it? We call it fatigue. I'm sorry, fatigue strength factor fraction. Fatigue strength fraction. That's a factor you need to look up from this curve. So knowing the f, you can calculate the FSUT, and then you have SE. If your sigma max, your stress, falls in that range, then life is going to be between 1,000 and a million. And then you guys have to calculate that using this formula. You know, we did an example like that in class. Right, so you find A and B, put the sigma here, you find the life. If, so that's one case. But what if the stress was actually higher? If sigma max was higher than FSUT, right? Then if that's the case, I'm falling here. In that region, you just say, you know what, I'm going to have finite life, and life is going to be, life is shorter than 1,000 cycles. That's it. You're done. You don't need to find the number. Just say life is less than 1,000 cycle, and you know, and life is finite. This is what you do. All right. But for our case, again, I repeat, we were here, so life is infinite with factor of safety of 1.03. All right. So I hope you guys find this problem useful. That was a good practice because it went through everything, right? We used Nerin's factor, bending moment shear force diagram. We used Q to find KF, and then it has everything, right? It has a lot of things in it. So I hope you find it useful.